So next is a very simple discussion about the validity of the first bond approximation. So we have already discussed in detail about the first bond approximation. So in the first bond approximation, the wave function takes this particular form. Now this form is valid only if the second term of this expression is very small compared to the first term. Okay, because it is basically we have truncated the series in the second term. We have not go to the third term and all. Okay, remember this is a series solution for the wave function, and in the series solution we have truncated, we have taken only the first two terms, we have neglected the third term onwards. Okay, so why we have neglected the third term onwards? Because even the second term is very small compared to the first term. So if the second term is slightly larger, or if the second term is dominant, then we have to take the third term also. So that means we have to go for the second order bond approximation. Okay, so the first bond approximation is valid only if this second term is very small compared to the first term. Okay, so the first order bond approximation is valid only if the second term of the RHS in the above equation is very small compared to the first term. First term in RHS. Okay, so the second term, what is the second term? The second term I can write mu upon 2 pi h cut square integral e raised to I k modulus of r minus r prime divided by modulus of r minus r prime v of r prime psi 0 of r prime dq bar prime. So this, the magnitude of this, or the magnitude square of magnitude of this will be very small compared to the first term, psi n of r square. Okay, now the psi in of r and psi 0 of r would be the same. So psi in of r and psi 0 of r, the incident wave function, and the zeroth order, the bond series solution, both are same as a raised to I k 0 dot r, that is already known to us. Okay, so and hence we can write it's equal to modulus of mu upon 2 pi h cut square integral e raised to I k modulus of r minus r prime divided by modulus of r minus r prime v of r prime. The psi 0 of r can be written as e raised to I k 0 dot r prime dq bar prime mod square would be much less than the psi incident is e raised to I k 0 dot r mod square. Now what will be the mod square of this? So this will give 1. Okay, now what would be the left side? So in left side we get the same, almost the same expression. Okay, so better we can copy this term to the next page, and we get the condition as it is. This should be much less than 1. Okay, now what is the maximum possible value for the left side? So the maximum possible value for the left side is possible for the region when potential is very large. Okay, when r is large, the interaction potential will tend to 0. So the potential would be maximum when r is very small. Okay, so the interaction potential is large when r tend to 0. So this we can put it here. So when r tend to 0, this integral become mu upon 2 pi h cut square integral e raised to I k r prime. So minus I k r prime divided by r prime. So there is no need to put minus because the modulus of r minus r prime. So when r tends to 0, the modulus of minus r prime would be plus r prime. So e raised to I k r prime divided by r prime, and then v of r prime e raised to I k0 dot r prime. I can write e raised to I k0 r prime cos theta, then d cube r prime mod square. That would be much less than 1. Okay. Again, we can expand your this d cube r prime. So d cube r prime can be written as d cube r prime is r prime square sine theta d r prime d theta d phi, and integration over phi simply become 2 pi. So that can be connected. So that 2 pi and this 2 pi would be cancelled. Okay. So if you integrate it again, so it's mu upon 2 pi h cut square integral e raised to I k r prime by r prime v of r prime, then integral e raised to I k0 r prime cos theta sine theta d theta integral from 0 to pi, and here is integration from 0 to infinity, then integral 0 to 2 pi d phi, then the entire thing have to integrate over r prime mod square is much less than 1. So this integration over phi, that will give 2 pi. So this 2 pi and this 2 pi would cancel. And what about this integration? I think it is already known to us. So this would give the fact that is become e raised to I k 0 r prime minus e raised to I k0 r prime divided by I k0 r prime. Okay. So then, so the next step, we can write this equal to modulus of mu by h cut square, because this 2 pi cancelled, then integral 0 to infinity e raised to I k r prime divided by r prime, then v of r prime e raised to I k0 r prime minus e raised to minus I k0 r prime divided by I k0 r prime square dr prime. Now this r prime cancels. Now finally, after a few simplifications, so this can be simply written as mu square upon h cut raised to 4 k0 square, then mod integral 0 to infinity. Now remember, for elastic scattering, magnitude of k and k0 are same, so this can be taken inside. So this would become v of r prime e raised to 2I k0 r prime minus 1 times dr prime mod square is much less than 1. Okay, now we have got the validity condition for the first order approximation. So for the first order approximation, this term, okay, so better I can write in another way. So this can be written as uh, uh, some 1 upon h cross square k0 square by 2m, and so 1 2 I have added, so 2 can be taken out, and 1 h cross square can also be written like this. Okay, so this term, then modulus of integral 0 to infinity, so integral 0 to infinity v of r prime exponential of 2 I k0 r prime minus 1 dr prime mod square much less than 1. Okay, now in order to satisfy this condition, the first thing is this denominator must be very large. Okay, now if you look at this denominator, it's a small correction here. It's not m, it is mu. Okay, so this denominator is compared, the expression is compared with the kinetic energy. So this corresponding to kinetic energy, and this corresponding to the interaction potential energy or interaction potential. Okay, now for the validity of this condition, the kinetic energy of particle, the kinetic energy of, more correctly I can write the incident particle, must be very large compared to the interaction potential. So this is the validity condition for the first order bond approximation. So if this condition applies, if the kinetic energy of incident particle is very large compared with the interaction potential, then the first order bond approximation is valid. Okay, so that's all about the bond series and the first order bond approximation, its validity. And so we are going to stop the discussion about the bond series with this lecture. In the next lecture, hopefully we'll discuss another method to solve the scattering problem, and which is called the partial wave analysis. Okay, so see you in the next class with this new topic. Thank you everyone for watching this video. Bye.